Now it's my pleasure to chair the plenary session that includes 4 world-leading experts. The primary aim of this session is to put the road mapping exercise in context of the broader energy field. Next slide, please. So before starting the plenary session, a little housekeeping. If we have time, we will have a question and answer session after the plenary talks. Please submit your questions during the talks via the question box. You may address your question to a specific plenary speaker or to all of them. Finally, could I kindly request that the plenary speakers complete their talks within 5 minutes. For now, it's my pleasure to introduce the first plenary speaker, Professor Clare Gray from the Chemistry Department at the University of Cambridge. Clare is a fellow of the Royal Society. She's a world-leading scientist in the field of batteries, having made seminal contributions in fundamental understanding of how batteries work using operando characterization, as well as many other discoveries in the field. So on to you, Clare. You've already got your webcam and microphone on, so please start.
Thank you. It's delighted to be there as the first speaker. Next slide, please. So what I'd like to do in my 5 minutes is just to pitch the fact that in order to make batteries applicable for the 2050 agenda, we have a lot of work to do. Next slide. So I think it's very important to remind people, first of all, why this is important. Everybody knows about the electrification of transport and the issues associated with the cost, for example, in cars. But the bigger challenge is how do you think about finding batteries for example, the lorries that will enable transportation of goods around the UK. And then the even larger challenge is how we use batteries for the grid. So we're not going to enable the use of the photovoltaics and the wind that Julia has talked about in her previous thing if we don't think about how we do storage. And we're in the position now where batteries are doing a good job for short-term frequency regulation, but if we're really going to make them batteries to have impact of those sort of hydro systems, then we really have to scale up massively and reduce cost. Next slide. So it's another important thing to recognize that we really are very close to the theoretical limits of the materials. And so we need, within the context of the 2050 agenda, to come up with radically new approaches if we're going to make impact. So the price of the battery has come back down by more than a factor of 10 since it was first invented, by new materials and some engineering. And the next improvements are largely going to be due to the scale, for example, of all the gigafactories that are being built around the world. But we're pretty much at the theoretical limit in terms of how much we can get from the materials that we're using in today's batteries. So we've improved from about a factor of 3 from the original lithium cobalt oxide systems to the NMCs and other systems like that. But if we're going to make changes, we're going to have to come up with radically new chemistries and get them to work in a cost-effective way and deal with the safety consequences. And this little laptop, sorry, the little Samsung Galaxy phone is just there to remind everybody that just even trying to get 10% or 5% extra energy density has resulted in safety consequences. Next slide, please. Then the other critical issue is sustainability and storage. So lithium and cobalt and nickel are all critical resources. And as electric vehicles are pushing away from lower cobalt to higher nickel contents, it isn't just the cobalt that is the issue, it's the nickel. And the resources are coming from parts of the world, such as DRC in terms of the cobalt. But in the lithium, there are lithium brines being mined in Chile and Bolivia, where they're some of the most driest parts of the world, and they have environmental consequences for the people who live there and the animals that are in that habitat. And so increasingly, we've got to change the way that we think about batteries, moving them to being inherently recyclable so they're easier to pull apart, and that's built into the whole design of the battery system. Next slide, please. So there are some simple ways to reduce cost. We can make cheaper materials. We can think about making bigger batteries, but there's tremendous materials challenges in how you design a system so that you can move the ions and the electrons in and get the same rate and deal with the fact that the batteries expand and contract throughout their lifestyle. And so there's a lot of fundamental science that needs to be done to determine or improve the way we control materials in non-equilibrium environments. And I'll touch on that in a minute. And then we have to do this in a much more efficient way. So the current battery assembly process in itself produces a lot of carbon during its manufacturing process. Next slide, please. So just to reflect on a few things, the first thing that we need to do is to stop batteries from degrading. And so the Faraday Institution is formed to inspire lead the UK's battery activity, particularly in the automotive sector, and I lead the Degradation project. And I think this is one of the critical ones because improving the lifetime of a battery is inherently important in terms of the sustainability and also the cost issues. Next slide, please. But it's not just about improving today's generation batteries. For the 2050 agenda, we have to come up with radically new systems. There are simpler ones, like trying to get materials of higher energy density to work, such as silicon, which in principle offers you, just based on the silicon, a tenfold improvement in volumetric and gravimetric capacity. Turns out that's less than a pack level, but nonetheless has to be achieved. A lot of challenges with it. Just to remind people, when you cycle a battery between charge and discharge, it operates outside its thermodynamic window. So the electrolyte and decompose as you're cycling to form this thing called the SEI. This continues all the time, and so that's a problem and a degradation issue that has to be solved. Next slide, please. We then need to think about, are there other systems beyond the traditional lithium ion? We could think about sodium ion batteries, good for the grid because they're cheaper. Magnesium batteries in principle give us highest energy density, but as we all know, as material chemists or physicists and chemists, it's much harder to move magnesium 2+ ions through solids. Turns out it's also harder to get them out of solution because they're well solvated. So a big challenge, but worth looking at in the 2050 agenda. Next slide, please. And then we need to think about radically different systems. So we have the lithium sulfur systems, where problems of the dissolving the sulfides are an issue, but we need new ceramics to address that issue. The lithium air space is sort of the highest energy density possible, has the same theoretical energy density as gasoline, both practically and theoretically, but lots of challenges because it brings us the challenge of a fuel cell and the battery together. Next slide. But progress is being made. This is just one little illustration of work by myself and Peter Bruce and others using redox mediators to help shuttle ions backwards and forwards, going closer to making this a viable technology. And next slide, please. Then thinking about solid state batteries for improving ceramics, again, thinking about from a fundamental level, how do you move ions across all these multiple interfaces? How do you deal with volume expansions and contractions? Next slide, I'm almost there, Manish. And then when you start really thinking outside the box, you need to move away from a confined system where the box is your electrochemical cell defines how much energy density you have. And if you have a redox flow battery, you can flow in as much liquid as you want to do the reversible chemistry. And it starts to make you link together a battery and fuel cell. And while these systems are not yet any cheaper than lithium ion batteries, they give you potential scalability. And I think they're very much part of the future and should be part of any research agenda, particularly for batteries for the grid. And we should do that in the context of new fundamental science. And so the next slide just gives you a couple of those. I would argue we need to understand how the processes from the atom level through the pack level work. We need to understand how you control materials under harsh and non-equilibrium conditions, and to understand and to control how we design interfacial processes. Next slide, please. And we need to do this via in situ metrologies to look at what's happening as the materials are operating. Next slide, please. And design new materials to make this happen. So this is just an example of some high rate materials for fast charging. And I just want to end with the final slide, I hope, by saying there's a lot of space out there for different chemistries and new science, but it's a really challenging process where we need to understand from the bottom up how to control metastable processes and non-equilibrium systems. So thank you very much for listening.
Thank you, Claire, very much. It's my pleasure now to introduce our next plenary speaker, Professor Jenny Nelson from the Physics Department at Imperial College London. She's the head of Climate Change Mitigation Team at the Grantham Institute, and her current research focuses on molecular semiconductor materials and their applications to organic solar cells. She became a fellow of the Royal Society of Chemistry in 2016 and was a recipient of the Faraday Medal from the IOP in 2016. So on to you, Jenny. Thank you.
Thank you, Manish, and thank you, Leeuw and others for the organization. Can I have the next slide? And the next. So, next please as well. So we've been, and next please. Thank you. So we've seen it has already been mentioned, the photovoltaic field market has been growing extraordinarily rapidly at a rate of more than 30% per annum over a couple of decades and more. This has been driven largely, or associated largely with reductions in the cost. And the market that we see is increasingly dominated by crystalline silicon technology. If we want to meet the low carbon targets expressed by net zero or other mitigation pathways, we rely on PV to continue to grow. And so we need to ask the questions, what are the factors that could limit the future growth in PV? Next slide, please. So we can identify three areas. One to do with the fact that solar is a variable resource, and so there's a danger of oversupply when the power can't be used. That increases the overall cost and reduces the value of the power. Then there are issues to do with the cost of the technology and to what extent that can reduce. That's a function of the module, but also of the way that it's integrated into the system. And then there are regulatory issues that will influence how fast and in what way the technology can grow. Next, please. So these involve, some of these involve issues for material science, not all. The cost of the PV technology particular is influenced by factors such as the electronic and optical quality and the stability, not only of the semiconductors that we use to harvest and convert the light, but also the materials that we use as contacts, as electrodes, as optical coatings, and the materials that we use as parts of the system. Next, please. But there are also materials science issues for the associated technologies which we will depend on in the end for integration of PV into the energy system. Clare mentioned the need for stable and high performance battery materials. Storage is a very important part of integrating PV. Then there are also the associated technologies of transmission, distribution, and the use of solar power, for example, in fuel synthesis, in transport, and so on. Some of these issues will be addressed later in this talk. Next, please. So thinking about PV in particular, and coming back to the road mapping exercise that Neil talked about, there's a number of directions in which we could go from the state of the art, which is crystalline silicon, which currently dominates about 95% of the market. And one obvious way to go is to try to make crystalline silicon technology better and cheaper by working on the manufacturing and the design of the crystalline solar cell to improve its cost effectiveness, extend its lifetime, and improve its efficiency. Next. We can also go in the direction of trying to make silicon better by adding something to it to increase the overall efficiency. And that could be, for example, as Julia Brown mentioned, a clever optical coating, which is allowing us to harvest more of the solar spectrum by down converting or even up converting some of the light that isn't efficiently captured by a solar cell. Or more obviously, it could be a second semiconductor layer, which acts as a second solar cell with a different larger band gap device to form a tandem and increase efficiency. Next. Or we could make a device which is inherently more efficient by using multiple gaps and not constrained by silicon. We could, for example, look at other material systems. Next, or if we go in a different direction, we could, rather than trying to increase efficiency for the sort of standard market, we could look at where PV can be used in other markets where different properties that aren't easily met by crystalline silicon are needed. For example, where you want to integrate transparent solar cells into buildings, or when you want a very light or flexible solar cells for use in unusual applications. Next, and probably most importantly of all, we should think about how to reduce in cost and improve overall performance by integrating the solar cell into other functions. For example, integrating a solar cell device with a catalyst for fuel synthesis, with a battery for any type of application where you wish to store and reuse the power. So I'm going to give just two short examples from this list. Next, please. And next again. The first example is to take something which is actually being developed and commercialized in the UK, the idea of putting an extra layer on top of silicon to turn, say, a 24–25% silicon solar cell into maybe a 27 or higher percentage tandem device. And that can be done by using a layer of a perovskite PV technology. Perovskites offer band gaps which are reasonably good to the optimum to make a tandem with silicon. And to do that, to do it efficiently and well, then there's a number of issues from material science. They're to do with controlling the defects in the perovskite, with trying to minimize the lead content. And then also work to do on the silicon, to do with its design, to do with improving the compatibility of its surface with the layer that will be deposited on top. And then we need to think about the manufacturing process, and to make sure that both in manufacture, in recycling and in use, exposure to toxic components is minimized and the overall embedded energy is reduced. So that's one sort of specific challenge. Next, and next again. So the second example I want to give is where solar cells could be used in non-conventional markets. And for example, there's a growing demand for PV to power small components, mobile components, for example, in Internet of Things. There's also another area, which is the use of solar power for satellites, for example, for the growing communications industry. That's a relatively high value industry. And the first IoT is something which is growing very, very rapidly. And here, because of the very different conditions in which the solar cells would be used, you have different requirements. On the semiconductor itself, for example, optimization in different spectral conditions, and also on other factors that we don't normally consider, like the power to weight ratio of the silicon solar cell, its mechanical toughness, and then of course we need to consider the usual issues of lifetime and production cost. Next. And again, these introduce some issues from material science, but they're rather different issues than the ones that we would need to consider, for example, in improving silicon, or for example, in putting perovskite on top of silicon. But they relate to properties of the semiconductor, design of the overall device, and of course the sustainability and embedded energy in the manufacturing process. So I'm going to leave it there. I'll be happy to take questions later. Thank you.
Thank you very much, Jenny, for that excellent talk. Now, it's my pleasure to introduce Professor Nora Leeuw. She's a professor in computational chemistry and the executive dean of the Faculty of Engineering and Physical Sciences at the University of Leeds. She's a fellow of the Royal Society of Chemistry and Learned Society of Wales and member of Academia Europaea. Her research encompasses materials for biomaterial applications and sustainable energy materials. So over to you, Nora.
Thank you very much for that introduction. I'd just like, with my computational background, like to show that computation, for instance, has quite a role to play in designing and improving sustainable energy materials. I mean, very much based on the concept of the Materials to Genome Initiative in the United States, where it was shown that if you introduce computation in a series of experiments, that you get products have a much shorter time from the lab to the shelf, so to speak. So I'd like to just show a few examples of where computation can help experiment and can actually be truly predictive as well in designing and developing new materials for sustainable energies. The reason I'm picking iron sulfides here is because, as we've already heard, there is a great need to look at materials that are based on readily available elements. And of course, both iron and sulfide are readily available and therefore cheap, and we will not be, and geopolitically, they're in stable countries. So could I have the next slide, please? So we had a look at a couple of iron sulfide for a number of reasons. First, there's an intriguing origin of life theory that posits that that's iron sulfide particles that were created in black smokers, either alkaline black smokers or acidic black smokers in the archaic ocean. Created these tiny little iron sulfide nanoparticles, and these were actually the catalysts in the origin of life. So they were catalysts for converting dissolved CO2 into small biological molecules, or well, it was prebiotic, so small organic molecules that eventually led to life evolving from the sea. Now, whether this is true or not, we don't know, but it's an intriguing concept, and we thought that iron sulfides, for many reasons, are interesting to look at. Another reason is because they have, in enzymes, you have reactive sites that are based on cubane iron sulfide and iron nickel sulfide cubane particles, where a lot of the electron transfer takes place, or again, which act as a catalytic site. So based on these two examples, plus the fact that, of course, iron sulfides with their multiple valence sites are very good electron cycling materials. So we were interested in looking at these to look whether we could convert CO2 into useful chemicals or synthetic fuels, which of course would be help a lot in a carbon net zero future. Could have next slide, please. So of course, one of the reasons why we looked at these materials was because they would be quite good for modeling, both modeling and experiment. And we were mainly interested here to also solve a problem in the literature, whether the alkaline or the acidic vents would be the best for this origin of life theory. So we started with the calculations looking at the three types of carbon dioxide molecules that exist in these three pH regimes. So in a very acidic medium, you would have dissolved CO2, and we absorbed those and calculated the binding energies to two major surfaces of these tiny mineral particles, the 001 and the 111 surface. And then in a pH 6.5, you would have bicarbonate, that would be the main species, and at a very high pH, it would be a carbonate molecule. So we then attached all these molecules. Well, we did some calculation of these molecules binding to these two surfaces. And if you look at the energies, you see that the bicarbonate and the carbonate both attach to the 111 surface and also to the 001 surface. However, in an aqueous medium, of course, it's a competition between the carbonate molecule and the water molecule. So if you look at the binding energy of the water molecule, it is from those comparisons clear that only the 111 surface, the bicarbonate molecule, can actually displace the water molecule from the surfaces, and therefore that should be the only catalytic regime where you could convert the CO2-based molecule to something else. Could we have next, please? Then we did the calculations of the mechanistic catalytic pathways, and starting from the adsorbed molecules at the surface, you go through a lot of intermediates. So this is actually a good slide to show that we need a lot of computing power. I mean, computing is obviously always thought like, well, it's a cheap technology. You don't need very heavy lab-based equipment, but you do actually need quite a lot of computing power. And we're fortunate in the UK that we have that through the Archer 2 and its predecessors, national computing facilities, which is a real help to make the UK internationally competitive on computational sciences. So we then calculated all these intermediates, and we calculated pathways, and then what we calculated was that you can get through the mechanisms within a reasonable voltage of about 1 volt, which we wanted to stay in a reasonable energy regime, so that this is a process that could be powered by solar energy, for instance. You could get both methanol and methanoic acid, which are very good either a fuel or a chemical itself, or a very good precursor to a lot of known pharmaceuticals, fuels, etc. Next slide, please. Of course, in the end, the proof of the pudding is in the eating. So we did experiment as well to see whether with these novel catalysts we actually did get products that we were looking for. And you can see already that the calculations were right in predicting that at pH 6.5 we would get the best catalytic performance. And you can see that we do indeed produce methanol and formic acid, but more interestingly, we also form CC bonds and have both pyruvic acid and ethanoic acid forming at pH 6.5. This is particularly interesting because pyruvic acid is accepted as a small organic molecule that is imported on the pathway to bigger biological molecules. Next slide, please. They've got a very quick, I promise it will be very quick, an example of another work where we worked with experimental colleagues in Eindhoven University looking at iron pyrite, another sulfide material for photocatalysis. It should be a really good photocatalyst, but it has experimentally shown limitations, even though theoretically its potential would be very good. Next slide, please. Now, originally, it was often thought that marcasite, which is the same composition but a slightly different structure, if you get inclusions in pyrite, that would bring down the potential of pyrite as a photocatalyst. Because an early experiment had shown that the band gap in marcasite is much lower than the band gap in pyrite, and therefore would make the material less well performing. However, recent theory and experiment both shown that the band gap in marcasite is actually much higher and similar to pyrite. So there is no reason why marcasite should have a negative effect on the pyrite material. Next slide, please. So we did an experiment, or rather my colleagues in Eindhoven did an experiment, and they showed that indeed if you have pure pyrite, which is the green curve, you have a moderate response to as a photocatalyst or photoelectrochemical material. However, if you have a mixed phase, I mean, they created two mixed phases at two different temperatures, the red and the blue, and you can see that particularly the red phase, which was synthesized at 380 degrees C, has a much better response, photo response than the pyrite material. So then the next slide shows some calculations be done to explain this and then look into why this could be the case. And when you do the alignment of the band gaps of the pyrite and the marcasite, so you take into account the vacuum level and then you just basically align the gaps, what you find is that you get this type of setup where if you had a photo excited electron, for instance, in marcasite, it would go to the conduction band, but because of the different alignment of the two materials, it would then actually flow into the conduction band of pyrite. Whereas if a hole is created in pyrite, it actually flows to the valence band of marcasite. So you get a very effective separation of the two charges, which is what is necessary in a good photoresponsive material. So in fact, the modeling here shows what was shown experimentally, or explains what was shown experimentally, that actually if you have a mixture of marcasite and pyrite, you should get a much better photoresponsive material rather than initially. So that was just the two examples I wanted to very quickly show, and I hope I haven't gone too much over time. Next slide, please, just to acknowledge the people who did the work. So Alberto and Nelson for the modeling, and Nathan and Longvei for the experiment. And thank you very much for listening. Thanks.
Thank you, Nora, for that very nice talk. So it's my pleasure to introduce the last speaker of the plenary session, Professor Stuart Parkin. He's an IBM fellow, an expert in magnetoelectronics and spintronics. Stuart is the director at the Max Planck Institute of Microstructure Physics in Halle, and a professor at the Institute of Physics at Martin Luther University in Halle, Wittenberg. He was awarded the Millennium Technology Prize in 2014 for his work on spintronic materials. So on to you, Stuart.
Thank you very much. I'm very pleased to say a few words about how we could potentially build more efficient electronics beyond today's systems which are based on charged currents. I'm just going to make a few comments then about potentially using spin currents and ion currents to build more energy efficient storage and computing technologies. So if you go to the next slide, then of course we're in a super exciting era of the silicon MOSFET, and over the last 40 years it's enabled orders of magnitude improvements in computing power In other words, we can compute much more efficiently in terms of the cost. And so this has led to an enormous improvements in our ability to, for example, to collect and analyze digital data, and it's really fundamentally changed the way we live. However, the concept of the silicon MOSFET has been to simply scale a device to smaller and smaller dimensions. And we've reached a point where in order to do that, we need to use increasing amounts of energy, so much energy that it becomes impossible. So the conventional rules of scaling CMOS devices, which have enabled these enormous improvements in computing power, essentially ended about 10 years ago, when we could no longer increase the frequency with which we operate transistors. So today, there are two main areas of very interesting research that could enable us to go beyond the charge-based CMOS electronics. And these, I think, you could imagine are quantum computing, and quantum computing uses very different principles, and a whole variety of quantum bits have been evolved over the last few years, including spin qubits, ion traps, and the leading technology today is superconducting qubits. However, quantum computing is likely to require today very low temperatures, and it's not something that we might imagine to be in everybody's pocket. However, at the same time, quantum computing is perhaps restricted in the types of problems that it could solve, although it could solve these with massive computing capability. Another very interesting area is what we might call neuromorphic computing or cognitive computing, where we imagine that biologically we can compute 1 million times more energy efficiently per computing operation than today's CMOS transistors. And so can we build new types of devices, new types of systems of devices that would be based on principles from nature? And this is very interesting and very exciting. And the concept is we could build a computing system then that would use 1 million times less energy to carry out the similar computing power. Again, the problems may be more restricted, but nevertheless could solve many of the computing problems that are important for our lives. So I like to call this possibly human computing era would begin. So my points today is that to do this, we probably want to go beyond the charge and perhaps consider spin currents, or we want to go beyond the charge and consider ionic currents. And I think another very important point is that today's computing devices, both for computing, for memory, and for storage, magnetic storage, are all innately two-dimensional. You have a sheet of transistors, or you have a sheet of magnetic bits. We want to build devices that are more innately three-dimensional. I think this will be a very important principle going forward. So if you go to the next foil, let me just briefly touch on spintronics. So spintronics is the notion that in heterostructures consisting of alternating layers on the electron scattering length scale of metals and insulators, non-magnetic and magnetic materials, we can build structures in which we can control the flow of currents of electron spins. An electron spin current innately can carry no charge, and therefore it can be dissipationless and therefore use much less energy. And the first device that uses the control of spin currents, or at least spin-dependent scattering of electrons, is something called a spin valve that I played a key role in inventing 30 years ago. And this has been used in magnetic disk drives to sense tiny magnetic fields, because it's basically the most sensitive detector of tiny magnetic fields that is known at room temperature. Although originally the principle was that of spin-dependent scattering, that giant magnetoresistance, the principle now has evolved to what is called spin-dependent scattering. And on the right-hand side of this foil, you can see what's called a magnetic tunneling junction. The blue and red layers are magnetic layers, and the gray layer is an insulator. The electrons can tunnel from one magnetic layer to the other, and depending upon the relative magnetic orientation of these two layers, the tunneling current can be high or it can be small. And today at room temperature, you can see changes in current when you change the relative orientation of these magnetic moments of the two layers of about a factor of, up to a factor of several fold. This concept of a magnetic tunneling junction then is very interesting. You have a device with two states which is non-volatile because it's determined by the magnetic moment of one of the layers, and yet the difference in the resistance of these states can be so large that it can be detected on very short timescales. This is the principle of something called magnetic random access memory, and it's something that we proposed in 1995. So on the next foil, I just wanted to give you some sense of how long it takes for a new physical phenomenon or even new material to make its way from the laboratory into a technology. On the top is just a time chart of how long it took to take what was the discovery of giant magnetoresistance, a very large change in resistance, but in very, very large magnetic fields at low temperatures. So it's not technologically relevant. But I was able to show we could see a similar phenomenon at room temperature in fields that were 10,000 times smaller and make it technologically relevant by using a phenomenon called spin engineering. We use the concept of coupling of individual magnetic layers through metals to create entirely new structures. We call them synthetic antiferromagnets. It only took a few years before we could take fundamental discovery to a product that could revolutionize magnetic disk drives, enabling their capacity to increase by 10,000 times in the last 20 years. Although even that technology now, it's reached the end of its roadmap. But on the other hand, if we take this concept I briefly mentioned of magnetic random access memory, which is based on really a spintronic phenomenon, we proposed this in 1995, but it was only last year, more than 20 years later, that Samsung announced the shipment of a high-performance foundry magnetic random access memory technology. It turns out it's an embedded memory technology. And another very important principle of this Spintronics is that we could use spin currents to generate spin angular momentum to rotate magnetic moments. And this is the principle of writing these devices. It's called spin transfer torque. If you go to the next foil, I want to briefly mention what I think is a super interesting new concept. It turns out I also proposed this. But anyway, I called it magnetic racetrack memory. And I proposed this about 10 years ago. And the concept is that this would be a three-dimensional memory where you have billions of vertical scanning nanowires. And in this magnetic nanowire, we would store information in the form of magnetic domains, pointing in one direction or the other direction. And the basic principle is by passing a current through this racetrack or this nanowire, we can move the information backwards and forwards. So this would be a three-dimensional storage class memory capacity of a magnetic disk drive, 1,000,000 times faster, 50 times less volume, and much more energy efficient. So if you go to the next foil, I'm going to not say much about this. If you go to the next foil, you will see that we have evolved this concept from 10 years ago through several stages of discovery, where we've discovered totally new principles that actually make it even more interesting than we thought, and we can manipulate magnetic domain walls in these nanowires 10 times more efficiently than we had imagined 10 years ago with new principles of science. If you go to the next foil, maybe I just make a couple of points about another concept, which is going back to this concept of neuromorphic computing. Just a general point, the way we build computing systems is very different from the way we think. Fundamentally, we think in a very parallel form. We integrate memory and processing in single devices or networks of devices, whereas conventional silicon-based systems are individual devices for memory and for processing, in fact, several types of them connected together, which causes significant energy usage, whereas the brain is much more energy efficient and is great for certain types of problems. If we go to the next foil, then just wanted to make the point that this concept of cognitive computing, many different ideas, even a magnetic tunneling junction can be built as a synaptic device to connect neurons, artificial neurons, but there are many other proposals over the last few years, many of them based on charge-based devices, but some based on spin-based devices, some based on ion devices. This is like an emerging field that could lead to hugely low loss energy electronics. If we go to the next foil, then I just wanted to conclude by saying I think there's a lot of opportunity to build low energy electronics by going beyond charge, by using spin currents, and by, for example, to build racetrack memory, by actually something I didn't discuss, but there are enormous numbers of new chiral spin textures that have been discovered in the last few years, which are very interesting to build, for example, a reservoir type of computing with regard to cognitive computing. And I think building synaptic functions in not individual devices, but looking at systems of devices connected in a three-dimensional way to look at their emergent properties will lead us to highly energy efficient thinking devices in the next few years. That was the end of my talk. Thank you.
Thank you very much, Stuart. Could I thank all of the plenary speakers for their excellent talks.